So your homework B is still out. A couple of notes about the spotlight presentations. So the room and the time, I'd like to change it a bit. I'd like to move this graduate banquet on Friday. There's some students.
EC seminar 4 to 5.
EC seminar 4 to 5. Yeah. Who will have to go to the EC seminar?
I'm on the second in the list.
You're the second one.
Present.
So you could do 3 to 4.
What was the time
It
for
was 5 to 7, but Bradley banquet is starts at 5:30.
I was talking about per person, how much time is 6
4
minutes,
minutes plus 1 question, 5 per person. There's about 24 presentations. If we are strict about the time, it will be done in 2 hours. If we're not strict about the time, it will be 2 hours 15. 3 to 5 is an open slot that we could do. Is there a presentation next Friday?
They still didn't send it, but they sent out.
What?
There might be no. They sent like 4 days.
Alright, so
So the EC seminar will end this Friday.
there are no more EC seminars after this. Oh, I suppose.
That is the last of this semester.
Oh, okay. Why don't we do this? Here's what I'm going to do. We'll proceed with the order that we have at 3 to 4. People who don't get done, come back when the seminar gets over. If we don't make it through everybody, we'll just do the same time next week. Right? So 3 to 4 is office hour anyway, and we'll just book back-to-back times and do something. Sort of, it's a random ordering, it's a luck of the draw. I'm not picking anyone to go first to 1 week, but if you're, I suppose what I could try to do is rearrange so that all the EC seminar folks are up in the 3 to 4. So why don't we do that? All the EC seminar people send me an email, and I'll put you up on this. So you are definitely and there'll be if there's enough of you, there's a random permutation, so I'm not picking anyone. Okay. So please do that, and we'll do that this Friday. Okay. Sound good? Any questions? Okay. All right. So let's pick up from where we were last time. We were talking about this idea that we're moving from linear classifiers to nonlinear classifiers. When faced with a data set that is not linearly separable, we already exhausted this one option, which was just generating new features, the quadratic, polynomial, linear existing features, go to some higher dimensional space, then apply a linear classifier in that higher dimensional space. The other option, which is what we started explaining, getting into last time, is construct what I called a natively nonlinear classifier, if you will. Something that is nonlinear in your parameters as well. And it's going to be harder to learn, but it's going to, if you're able to sort of, one of the benefits of linear convex classifiers is that you can sort of operate them out of the box, right? You download a toolbox and they'll sort of give you some baseline performance. Here you'll have to know something about the domain and you'll have to do some extra work, but if you're able to do that, they'll often outperform. Okay. So last time we started talking about the neural metaphor, if you will, the neural network. There's biological neuron, maybe an artificial neuron. The idea was that linear combination of your input gives you an activation, which you then pass through a nonlinear function that gives you some, right? And we talked about different kinds of neurons, like you can have a linear activation function or a response function, or you can have a sigmoid response function, and we talked about a step response function as well. So these are all sort of linear in the input and then pass through some potentially nonlinear function. Right? And we talked about how a single neuron is still learning a linear decision boundary, right? You're still doing W transpose X, if you will. And so one way of getting around that is we had constructed this sort of multi-layer perceptron is what we had called it, because each unit we were calling a perceptron. It's a bit of a nomenclature stretch, because perceptron, if you're trying to be specific, refers to a unit with a step nonlinearity. So when we say multi-layer perceptron, we're actually not being very accurate in our use of perceptron, but let's sort of accept it. When people say multi-layer perceptron, what they really just mean is a neural network, a feed-forward neural network with some number of hidden layers and some nonlinear functions in it. Right? They're not always specifying the nonlinearity. So this is a 4-layer neural network. There's an input layer, there's hidden layer 1, hidden layer 2, and there's some output layer. Each sort of neuron computes a linear combination of its input, passes it through some nonlinearity, passes it forward. Right? So the output for this becomes the input for the next layer, and so on. Right? This is what we had looked at last time. And so if you think of this, all of up till here as a box, right? What you can think of is this is a feature extractor. This is creating, taking your input and passing them through some functions, which are again passed through some function. It doesn't matter how many times you pass it through, right? You can think of this as some sort of feature extraction process that you're doing, that you're going to then follow up with whatever task that you're interested in. Regression, classification, whatever. Right? Does that make sense? The key intuition here is that the feature extraction process is also learned. Right? Every neuron here has its own set of weights or parameters. There's as many as the height or the number of hidden times the input coming in, because every neuron has, every edge basically here has a number associated with it. Right? So all incoming edges here are the weights associated with this neuron. And so the number of hidden neurons times the number of previous layers, that's the parameters in this layer. Number of hidden neurons in this times the number of inputs, that's the parameters here. And you're tweaking all of them so that it helps, so that it learns a representation which helps the ultimate classification. Does that make sense?
The number of perceptrons in all the layers are same?
They don't have to be. There's very little restriction here on the kinds. The architectures that we'll study will mostly be feed forward, no skip layers, these kinds of architectures. We won't specify how many hidden units in a layer or how many layers. All the algorithms that we write down will be indifferent to that. In practice, you're going to set up some reasonable numbers, and there's no well-defined theory for what is a good feature representation. Right? So you should think of this as, I have some d-dimensional or p-dimensional features. How large do I want the features to be? There's no sort of well-defined theory. Does that make sense? And we talked about sort of this universal function approximator theorem. We didn't actually prove it, which is actually not completely non-trivial to prove. But you should know the fact that even a single hidden layer neural network with sufficiently many neurons in it can approximate to arbitrary accuracy any smooth function that you're trying to approximate. Right? So that means that we're dealing with extremely powerful machinery here. Okay, so the goal for today is, how do we set all of these parameters? Right? How do we, it's parameter learning, right? How this parameter, this parameter, this parameter, this parameter, this one, this one, this one, all of them jointly, how do we tweak all of these knobs so that we do well on some task? We'll define some loss function. The algorithm is going to be gradient descent. We'll define some loss function. This will be, all of these will be our parameters. We'll compute gradients of the ultimate loss function and just take a step in the direction of the gradient. Right, so it's going to be a gradient descent algorithm. The key problem is going to be, gradient descent by itself is extremely simple. You've already implemented it for logistic regression. I mean, if I freeze this box out here, this was with a sigmoid unit, just a logistic regression thing, and you've already computed gradients for that, and you know how to implement that. Right, so the key thing will be, how do we compute, if you think about this number on this edge, if I change it, it changes the output here, which changes the output here, which might change your decision boundary. Right? So it's going to be, how do I compute how much of a change here, how does that change the loss function? Computing that gradient is going to be the key sort of task for us today. That's done with an algorithm called Backprop or backpropagation, which is basically nothing but chain rule. Right? Gradient of this is gradient of that, gradient of with respect to something else, and so on. Right? It's just chain rule of computing derivatives. And that has a name called Backprop because it has natural intuitions with respect to backpropagation. We'll talk about that. Okay. So let's start with something which is simpler, which is forward. So let me actually. So if you sort of the notation that we'll follow, so these are the x0 feature, x1 feature, all the way to xd. So this is sort of the input layer, which I can represent as a vector. There is some neuron here, A1, which gets all of these as input. And there's not just one, there's A2 all the way to AM. Right? So this is my hidden layer. All of these are connected. So these are often called fully connected layers because every previous layer is connected. Every neuron in the previous layer is connected to every neuron in the next layer. So these are fully connected layers. So this will be my activation vector, if you will. There may be multiple of such layers, but ultimately there will be some output, right? So my notation will be, I'll call it A, O, or A out, and ultimately that produces, so in this case, there's some nonlinearity here, H1 through HM, and there's typically a sort of bias introduced at every layer. A bias feature introduced at every layer. So y hat is equal to G of, so that's the notation that we'll roughly follow. The way to think about this in terms of let me draw a single neuron zoomed in. So this is, let's say, AI. Right? One of these neurons I've sort of one of the neurons here I've sort of zoomed in, and there's going to be sort of x0 all the way to xt here. This number is wi0. This number is wi1 all the way to wid. Right? So these are all the scalars, which are the weights on the incoming edges of the ith neuron that I have. Right? And I'll think of this wi0 all the way to wi as the weight, the ith weight. It's the weight vector associated with the ith neuron. So there's a weight vector here, 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 associated with all the incoming edges. Does that make sense? And we're grouping all the incoming edges because they all affect a single activation. Right? We're not grouping all the outgoing edges.
What is that symbol after the D? RD?
RD plus 1. Because I was counting from 0 to D. Just a box. That makes sense? Okay. So here's one way of thinking about it. So this was the input. If you need to compute all the activations simultaneously, this is a vector, right? This is A1 is W1 transpose X all the way to WM transpose X. This is the vector of all the activations. Mm-hmm. And I can think of this as a matrix multiplication, right? What I can do is I can store all the store W1 on the rows, all the W's all the way to WM. I can store it on the rows, and I can multiply that by this X vector. Right? So each neuron has its own weight. Transpose that with X, you get a vector of activation. Does that make sense? That's how you get this vector of activations. In order to get the responses, you need to pass these activations through some nonlinearity, right? That's the function G that we're calling. And so what the notation that we're going to use is, so actually I'll do that here. So I'll say HI is equal to G of AI, which is the same thing as G of W transpose I transpose X. And similar to the activations, what we'll try to do is we'll try to construct a vector of all the responses. So G of A1 all the way to G of AM. Yes?
So every activation of the activation vector has one vector weight, one specific vector weight?
Yeah, so every neuron here has a vector weight associated with it. So what it does is it multiplies that with the incoming feature. I didn't write that. So AI is equal to, I did write that. Oh, good. AI is equal to WI transpose.
So all the features will have the same weight for one activation, for one single activation, right?
So let's pick AI.
Mhm.
All the features will have different weights, right? That's what this figure was. So this is a single neuron. These are all the incoming features,
Okay.
and there are different numbers on each edge,
Mhm.
right? And that's what this subscript was indicating. It was for the ith neuron and the dth feature.
Yeah.
What's the weight? Does that make sense? Okay. So basically, what I'm trying to draw here is this idea of forward propagation. Like if you want to make a prediction, you take your input and you propagate that information forward. And each propagation consists of two operations. This is a matrix multiplication, right? You take all your weights, multiply your features, you get activations. Pass all activations through a non-linearity. That's your hidden responses, right? You know, if you want to compute, this is one step, this is another step, this is the first step, right? If you want to compute A0, that's just W0 transpose H vector, right? Which is another, it's a vector multiplication, not a matrix multiplication, but that's because we only had one output here. If we had multiple things here, it would again be a matrix multiplication. And then finally, y hat is G of A naught, right? A naught. So it's a sequence of operations. Matrix multiplication, non-linearity, matrix multiplication, non-linearity, and you can have multiple such layers if you want. Right? And this is known as a forward pass. That's how you feed in an input and you get an output out. Does that make sense? What we're going to do next is we're going to tell you how to derive gradients of. So this is how you get an output, and that output may not match what you'd like to see, right? So it may not be the correct answer, if you will. And so what we're going to do is we're going to define a loss function that measures, for example, so loss between ygt and y hat, right? What did I predict and what did I want to predict? And what we're going to do is we're going to compute, so y hat is a function of all the parameters, and we're going to compute the gradient of this prediction, of this loss with respect to all of these parameters, and take a step in that direction of the gradient. Right? And computing that gradient is going to involve something known as backpropagation. Because computing activations, we work from left to right. Computing gradients will work from right to left. It'll be the easiest to compute the gradient with respect to this weight, and then finally this weight. And if there were multiple layers, one step at a time. Does that make sense? Okay. Okay. Visually, this is often what it sort of looks like. The green arrows indicate this. You think of this as information propagation in this network, right? So you start with some inputs, and you basically compute the activations, pass them to the nonlinearities, and they become inputs for the next layer. Compute activations, pass them to nonlinearities, and those become input for the next layer. Compute activations, nonlinearity, and that becomes your final prediction. Right? So you can almost think of a sequence of operations that you're doing, which depends on the size of your network, right? And modern sort of neural network libraries will often let you write code for one layer at a time. So you basically define what sort of layer you want to do. This would be a fully connected layer. It's connected to all inputs in the previous case, and you sort of write forward propagation code and you write backward propagation code. The backward propagation code will be called for the gradient descent part, and the forward propagation code will be called for sort of making predictions. Right? And if you just write that bit of code, most of the infrastructure around it will sort of take care of making predictions. And right? You can think of swapping this layer in and out for something else, and the same thing will work. Does that make sense? Okay. So let's get to gradient ascent or descent in this case. Let's define what we mean by that. So, very first thing, what do we want to learn? What are the parameters under our control? Here are all the parameters under our control. Right? So there's W1 to Wn, right? The hidden layer parameters. That's all the weight vectors here. And each one of them, as I mentioned, is an R of d plus 1. And there's a WO, thank you, which is R of m plus 1. Right? I'm doing this derivation for the simple case when you have a single hidden layer. If you have multiple hidden layers, the derivation just becomes slightly longer, right? So chain rule becomes slightly longer. Okay? So these are parameters under our control. We'll sort of call them theta, if you will. These are all the parameters. Does that make sense? We know that whatever prediction you make is a function of these parameters. Right? These are knobs that you can control. Right? I've given you a data set. What is given to you is usually a data set. X1, Y1 through Xn, Y. Here's what we'd like to achieve. So you go ahead and you define some sort of a loss function, right? And we've seen enough loss functions in this class to know what they roughly look like, right? Here's what loss functions usually look like. You basically sum over. There's some loss part, but you sum over your entire data set, and you basically compare yi, the reality, to what you actually ended up predicting, right? And there's usually some regularization. Right? This is sort of, we've seen enough of these examples that here's what I predicted, here's what the reality was, how do you penalize me for that, and I prefer some simple models, right? So therefore there will be some regularizer. The simplest regularizer that is often used is just look at the L2 norms squared of this vector, right? All parameters, we just like it to be small norm. We've seen that enough times. This loss, if we're trying to do regression, we know that simple loss here is least squares, right? So just do half yi minus y hat I of squared. Right? So this is the least squared loss. Right? You can also feed in the log probability so if you're doing classification, so this is for regression. For classification, you might also want to do 1 over n summation I from 1 to n of negative log probability of y equals little yi given xi over theta. Right? This might be our loss function. This is maximizing the log likelihood, right? How much does my model believe in this data set that I get? Okay. And we've written this for if this is a 2-class logistic regression problem, we know what the probability of 1 is, right? It's just 1 over 1 plus e to the negative of w transpose phi of the last layer. Right? We've written this down for a logistic regression. So plugging that in, that's just some function. That makes sense? So let me do this. We'll work with the least squares loss because it's simple. It's not too many exponents and things. It'll be easier to work with. So what I'll do is I'll pretend that we're training this neural network to output for a regression problem, right? And we're measuring loss with L2 loss. And I'll actually assume that this regularizer doesn't exist, right? Because it doesn't really matter. All we're going to do is take the gradient of this loss with respect to theta, and we know how to take the gradients of this. It's the gradient of this part that's the problem, right? But essentially the algorithm that we're going to follow is going to be initialize theta, take a step in the direction of the negative. It's just simple gradient descent that we're going to do. Initialize the vector theta. It's all the parameters. So randomly initialize the parameters of your network. All parameters here and all parameters here. Compute the gradient of the ultimate loss function. Finally, what you care about, and take a step in the direction of the negative loss because we're trying to minimize the loss. Right? And that's why I'm not going to focus on the L2 loss. Like, we know what the gradient of that is. That's not going to be the hard part. The hard part is computing the gradient of this with respect to all the parameters. Right? And the algorithm for computing this gradient is called Backprop. Okay. All right, so let's do that. So first, let's make life a little simple. Right? Let's start with a simple case. Let's assume that there's actually no hidden layer. Right? That's a really simple case. All inputs are connected to the output. Right? We already know this case, but it'll be nice to write it down in the notation of a neural network because then we'll be able to plug this in. Okay? So y hat is equal to g of a naught, which is equal to just w out transpose x. This is what happens if there is no hidden layer and you're trying to do regression, right? And this is a linear function, right? That part's pretty simple, right? This is just linear regression in x, and the loss function with respect to all theta. So the only thetas now are the w out, right? There are no hidden parameters, and that's 1 over n summation of half I equals 1 to n yi minus y hat squared, and that's equal to w naught transpose x. Right? I know how to take the derivative of that with respect to w0. It's just 1 over n summation of I equals 1 to n minus of yi minus w naught transpose x times. Leaves a weak x transpose. Right. Squared loss, chain rule, x squared becomes 2x. Right? Right. Excellent. This is error. Right? What were you asked to predict and what did you actually predict? And this is the pattern or the data, right? This is exactly what we did in logistic regression case as well. If you remember the gradients that we derived for logistic regression, they looked exactly like this. Take a pass over your training data set, compute how well you're doing on this each point, right? This is what you were asked to predict, this is how well you're doing. And take a step in the direction of this data point proportional to this error. So if you're making a lot of mistakes, you take a large step in that direction. If you're not making any mistake, if this error is 0, you don't care about this data. Does that make sense? So this is exactly that, right? And this is, if you were implementing, where did the algorithm go? Right, so the algorithm that you were implementing would be gradient descent. So w naught t plus 1 is equal to w naught t minus eta of del. This is what you would write down. So if you were doing batch gradient descent, you would compute this gradient by one pass over your data set. If you're doing stochastic gradient descent, you would say, I'm just going to sample the data point, and every data point gives me a gradient, and I take a step in that direction. Does that make sense? Okay. So we already know how to do this for a single layer neural network. Let's bring in the sort of hidden layers back. A naught all the way through AM, right? This part doesn't actually change if you think about it, right? All I did was, what did I compute? I computed derivative of the loss with respect to the output weights. Right? That should actually stay this. Yes. So this should become h. Right? And we'll actually write this down and show why this becomes h. Does that make sense? If you think about it, the input to this layer is actually h, and that's what it should be. Okay.
H inside.
Yeah, and an h inside as well. So this will be hi as well. Okay. So here's how we're going to compute gradients with respect to every single parameter. There is an A naught here, there's an H here, there's an A here, and there's, so the weights are, let me write with special color, the weights are W naught here, and the weights are Wi here. What we're interested in are the gradients of the loss with respect to these two. But we're going to do something extremely weird. We're going to start computing loss with respect to the gradient with respect to this, A naught, and we're going to start computing gradient with respect to AIs. And what we're going to do is we're going to work our way backwards. So first we'll compute gradient with respect to A naught, then W naught, then AI, then WR. So instead of computing one gradient, which we were interested in, we're computing 4 gradients along the way. And the reason why is going to be chain rule. We need those gradients as intermediate steps in order to compute this gradient. And it's actually going to be helpful to cache the gradient here and here, because we will make repeated calls to those. Does that make sense? Okay. So let's go here. So step number 1, so actually let me write numbers here. This is going to be 1, this is going to be 2, this is going to be 3, and this is going to be 4. Right, first we're going to compute gradients of this, and this. So let's do that. So the loss with respect to A naught. And let's, if we are comfortable with stochastic gradient descent, let's consider a single sample, right? Let's not assume the summation over n. Nothing changes. Instead of a single data point, you just end up with a summation. But the notation ends up being about T. Okay? So what is loss? Loss is basically y minus g of A naught, right? Half of this. Right, so the so gradient of loss with respect to A naught, and if this is a linear function, it's just y minus A naught, and so I just get negative of y minus A naught times no, I actually don't get that because g of A is 0. Yeah. Okay, so that part's pretty easy. This is step number 2. So now that we've computed gradient with respect to the output activation, we'll compute gradient with respect to the output weight. And that's where you'll see the first application of chain rule. So the derivative of loss with respect to W out is equal to derivative of loss with respect to A out times A out divided by. Does that make sense? That's just chain rule. You want to differentiate some quantity with respect to this quantity, you can introduce a new quantity. So how much does this affect that, and how much does that affect this? Right? The thing that I the thing that I cared about, you get to perturb W0 by something, and it has an impact on A0, right? So W0 is the vector here. If you change it a little bit, it changes A0, and therefore it changes the loss function. Right? And the key thing is we've already computed this. See step 1. Right? And computing this is pretty easy. We know that A naught is just W naught transpose H, and therefore this is just H.
We are assuming linear activation functions.
For this, yes. We're assuming this is the output activation function is linear because we're doing regression. If the output activation function was not linear, the only thing that would change is there would be a term here called G prime. Right. Nothing would change.
Y minus?
Y minus, because there's a minus here.
No, Y minus G of A.
Oh, sorry, yes. Thank you. Not that Y. WH1. Okay, so we've done step 1, we've done step 2, and we're going to do step 3, which is in substance, the most involved step. Because step 4, you know what's going to happen, right? I'm going to try to differentiate the loss with respect to Wi. So actually, let me just do step 4 first. It's actually the easiest step. So I'm going to try to differentiate the loss with respect to Wi, and I'll just end up writing that as loss with respect to AI and AI with respect to Wi. Chain rule again. And what I'm going to say is that this is what we computed in step 3, which is what I skipped over. And this is again pretty easy by the same argument as you know, AI is equal to AI is equal to Wi transpose Xi, and therefore this is just Xi transpose. And so actually, even though I haven't told you what step 3 is, step 4 already tells you that it's a good idea to proceed in these steps. Because if you think about it, this, the gradient with respect to A is used for all of these W's. And if you had any layers before this, they would also be using the gradient with respect to AI. And if you change the parameter before this, it would obviously change all these activations. And therefore, what we would need to know what happens ahead of the network to be able to cache it. Right? So, sort of the benefit of back propagation comes from the fact that you could have applied chain rule here first. We could have said, I don't care about these steps. I just want to do this first. Right? This is what I care about. I will derive it. What you would have ended up with is, okay, if you want to derive that, compute this. If you were to compute this, you will sort of start propagating forward. So you end up with a bunch of terms that all of these expressions are sharing. And therefore, it is better to work your way backwards and cache everything that is in common. Because everything ahead of a layer is shared by everything behind it before. Does that make sense? Okay. So let's do the most involved step. And by the way, this is going to be this is it. Like the class is easier after this. Okay, so just hang in there. I realize this is difficult, so I got a couple of videos after this. So it gets easier after this. All right, so let's do the loss with respect to AI, and we're going to apply chain rule. So we're going to say the loss with respect to A0 times A0 with respect to AI. And this is going to be already computed in step 2. Step 1. Already computed in step 1. Right here. And this is going to be the part that's somewhat that we have to compute. So we know that A0 is this guy. It actually is linear combination of all these H's. So I can write summation of WOI HI, I going from 0 to M. Right? Soon. It's almost done. I know HI is just the activation AI passed through this function G, and I'm being asked to compute the gradient of this
quick
thing.
question. So is this G the same function as the last step? G?
It doesn't have to be.
Doesn't have to be.
It doesn't have to be. I'm maintaining clean notation by not saying G of O and G of I. So in your head, you can think of every single neuron has its own G, but I'm being loose in my notation because if I start having subscripts for G's as well, it'll just be madness here. Okay. So there's this is what we're talking about, right? How much does this output activation change if I change one of these activations? There's only one term that depends on AI, right? So the derivative of this AI is not that, it's just W O I O too many I's is G. Yeah, much better. So W O I G prime. Does that make sense? A bunch of terms j is going from 0 to n. I is the neuron that we're interested in. So I come to you, and there's this expression which is summation of 10 things. And I say, how much does this expression change if I change the 9th thing? Right? And so you say, okay, the first 8 and the last one doesn't matter. So it's only the ith expression that matters. Here's the number, and here's the gradient of this function, whatever that is. Right? Okay, so that seems extremely obtuse. What is this, and what does this mean? Why did we do any of all of this? So if we come back to this quantity that we were interested in, it is gradient of the loss with respect to this activation, right? So let me draw sort of AI and WI. So all the weights leading up to AI, it produces an output, goes to equal, produces this. Right? There's a number here called WOI. If you stare at what we have actually done, we have computed, we've basically said, take the output take the gradient with respect to this output, multiply it by that number, right? How strong is this connection, and what was the gradient happening at this connection? So if you think about what's happening, we're trying to decide if I change the weight vectors here, how much does that affect the loss of this prediction? Right? And the way that affects is, well, how much does that change this activation, and how strongly are you connected to that activation, and how much do you change this activation by this weight vector? And that's essentially those 3 terms that we end up writing. This term and this term, which is a function of those 2 terms. Does that make sense? So it's a fairly intuitive interpretation. You want to change this, how much does that change this? How strongly are you connected to something in front of you, and how much does that change that? Okay, let's take a minute here and then we'll see sort of illustrations of this.
Isn't the loss supposed to be the sum of all the answers?
So this is sum of all things, but you take the gradient with respect to any one.
That's for one letter, right?
That's for one data.
The number one equation, the loss is for one.
One data, yeah.
But the loss is supposed to be sum of
Sum overall. So what I said was that assume you have one data point, you will compute this gradient. The gradient for all the other data points will be just the sum of things. Because the gradient is just the loss is a summation, and so the gradient is.
Maybe tomorrow. You tell me.
Okay. Alright, so what did we do? What we did was basically derived, and in some sense the actual numbers or expressions are derived aren't all that interesting, except to show you that look, chain rule is possible and calculus can be done in chain rule, right? That's essentially the purpose of sort of exposing this to you. I could have said that look, go look in the book, but none of you would have. So I at least ended up forcing you to go through this experience. That can be done. And in your head, what you should think of it is as this to this is just some function, right? It's just matrix multiplication passed through some function. This to this is some another function. And therefore, if I want to know the gradients of this, I can just sort of apply chain rule to everything and I can compute all the gradients. Here's a nicer way of saying that, much more polished way of saying that. This was, let me see if this thing is.
The net
So this was a network which was trying to do text to speech. This was a neural network trained back in the heydays of neural networks in the 80s. And the goal was the input here is some text sequence, and the output is you have to produce a phoneme that sounds like how somebody would pronounce it, right? And this is an explanation of Backprop made for the masses, and see if you can spot where they explain Backprop. And because they do, they ultimately go
was
to
called net talk.
Join the fun.
You're going to hear first what the networks.
that's Terry Sinowski, who is now the head of the NIPS organization, which is the main machine learning conference.
Sounds like at the very beginning of the training. And it won't sound like words, but it'll sound like attempts that will get better and better with time.
That's speech generated from a network that is not trained. Yeah, it's just random initialization.
The network takes the letters, say the phrase grandmother's house, and makes a random attempt at pronouncing it.
Spotted forward pass.
Grandmother's house.
The phonetic difference between the guess and the right pronunciation is sent back through the network.
My grandma came down. Grandmother's house.
By adjusting the connection strengths after each attempt, the net slowly improves.
And finally, after letting it train overnight,
This has been a history of neural networks. Anybody says, I want to train a network, yes, will you leave it on overnight? That has now turned into, let it run for a week and come back and do something.
the next morning, it sounds like this.
Grandmother's house. I like to go to my grandmother's house. Well, because she gives us candy. Well,
Net talk understand
I don't know how it became German in the process. So you spotted an explanation to the masses of basically Backprop. You take basically a function composition or an output which depends on an input which is based on some weights. You backpropagate to basically try to assign what is the gradient of each one of those edges, how should I change it, and you hopefully make an improvement to some objective function. And this was, to show you, this was for a while some of the best performing systems on OCR or optical character recognition, not through multi-layer perceptrons, which is what we looked at, but through something called convolutional neural networks, which is, let's see. So there's this system called LeNet for Jan LeCoultre, where this has been an interesting trend in neural networks where you end up naming an architecture after yourself, which is quite nice. There's now the AlexNet. Actually, you don't name it after yourself. Somebody else calls it your network, and then it just comes out here. So this is an architecture that we'll talk about in a bit. This is, the input is shown here, and these are the hidden representations. And what's happening is that there are different kinds of inputs coming in. This is a 2D input. This is not a one-dimensional input. These are characters, and it's the output that it's trying to get to is the ID. So it's just 1 through 10. What these are showing are each one of these is a hidden activations of the responses for this input. And the interesting thing that this sort of system extremely early on demonstrated that a lot of them look like basically gradient computations. They're 2D gradients. They're trying to look at horizontal edges or vertical edges in the images. Even though this system doesn't actually know it wasn't told to compute gradients, right? Gradients and 2D edge computation is one of the most elementary stuff that any computer vision system does. All of this was just fed into an output loss layer, minimized loss, right? These are all parameters that you can tweak. And it ended up in the early layers computing these elementary quantities which are gradients, which is an interesting thing to observe that this phenomena sort of emerges on its own. Right? Let's come back to this in a second. Here's a picture that I like. This is that's someone called Frank Rosenblatt. I think back in the 50s. I think this was a lab at Cornell. This is a neural network. It's randomly wired. This is before the era of computers, right? So everything has to be done in hardware. This is him holding a layer, trying to inspect the weights that his network has learned, because every layer is a physical device. It's a motor. Backpropagation is changing the tension in the motor. Right? That's how he's looking at the weights. And this is the network that he's training for his class. Oh my god. This is, you guys think that math was hard, try implementing it in hardware. So this was done extremely early on, and it had...
Can you tell the flow of numbers?
Yes.
So just by
He could do infinite precision. The thing to remember in all of these things is when we wrote down the network, you guys did gradient descent for maximizing the log likelihood of a logistic regression. We told you use a constant subsize, you will converge, which is nice because that function was convex. You were minimizing a convex function at the optimum. When the gradient vanished, you were guaranteed that you had found the global optimum. All of those guarantees go away here. Any reasonable sized architecture, as soon as you have a few hidden neurons, you're going to end up with a non-linear loss function in those weights, right? So even though you can implement gradient descent, and you may actually converge to some local minima, it's unclear whether what the quality of that with respect to a global minima. Right? So optimization issues become extremely difficult. So gradient descent will get stuck in a local minima. It's hard to often set a learning rate, which is that step size constant that we talked about. For convex problems, there's nice theory that says as long as you set a constant learning rate, as long as it's less than something called the Lipschitz constant, you will converge. And none of that theory exists for non-convex functions. Selecting the number of hidden units and layers is itself a black art. It's sort of one of those things where, how many neurons should I choose? Try 20, and if it works, great. Try a few more. If it doesn't work, scale back a bit. How many layers should I use? Anything more than 2, and now you're in the realm of deep learning. Anything less than 2, you're still doing old-fashioned neural networks, right? We know how to handle that. But there's no sort of principal guiding factor of, here's the optimal number of layers. Usually the way these things are done is, you're probably add one layer or a few layers at a time, and you know that it's a larger model class, and so you're looking at training error and validation error. If validation errors start going up, that's when you overfitting. Right? So usually these things require a lot of training error. And so what becomes important are these issues of regularization and early stopping become extremely important. There's a really nice paper that I put a link to on the class website. Here's a citation, and it's called Efficient Backprop, but it's full of these nifty little tricks of how to really make Backprop work. And the idea is that, this is an example, and I'm showing you an example. You and I, mathematically, this is a logistic, right? You can write down a logistic. And a logistic is perfectly fine, but in practice you should never use a logistic. You should use something called a tan edge, or sort of a scaled logistic. It's sort of shifted down and it's scaled a little bit. One of the reasons why you want to use this sort of a function and not this sort of a function is the output of this function is always positive. And so the responses that any layer gives you are always going to be positive. What you'd like to do is have the responses be zero mean. Right? And that's something that this sort of a function will roughly try to do, because it's symmetric around 0. It has positive values, it has negative values. Mathematically, this is just a shift down, scaling a little, but this really makes a big difference. One of the things that also makes a big difference is recently there's been this thing called the rectified linear units, and these things play an important role. So this is the sigmoid nonlinearity. Instead of that, this has worked really well. This is called the rectified linear, which is an odd name because it's a non-linear thing. Anyway, I guess the thing is that this is a linear function rectified to the positive. I don't know the exact intuition behind it. But it's a hinge-like function. It's 0 when the activation is negative, and it's max of 0, x basically. If the activation is positive, leave it untouched. If the activation is negative, clip it to 0. And this works a lot better as a non-linearity than the sigmoid nonlinearity. At first, it doesn't seem intuitively clear why it would work so much better. Any guesses or intuitions? You are not Jeff Hinton. So here's, did you have something?
The logistic regression never reaches 1 and 0.
That's one thing that we talked about, this type of a loss, but so what? Exploding gradient. Exploding gradient, almost, not quite, it's the opposite problem. So if you stare at this function, if your activations are really high or they're really low, right? If you start with random initialization and it lands you in an area where you have really high activations and that's really wrong. What your network wants to do is come back to the negative activation zone. The gradients are almost zero, right? So it takes you a long time. So the gradient here is almost zero and the gradient here is almost zero. Most of the gradients are present only in this linear range, if you will, of the sigmoid function. And so it's extremely likely that when you do random initialization, you will end up with a few units that are just saturated. And they are not going to change, even though they are completely wrong. The gradient is coming through from the next few layers. Hey, change this activation. This really needs to be negative. But the gradient with respect to this nonlinearity is just zero, right? So it can't propagate anything. That's the benefit of having a linear function like that. You end up never having saturated gradients. This is just an intuition. There is no sort of, I've seen experiments, I've seen some sort of justification, but there's no sort of proof that says this will always converge faster than this. One additional benefit of this is that the gradients actually, as he was trying to illustrate, the gradients actually become exactly zero at some point. And so if you're trying to do back propagation at any level, if the gradient becomes zero, you know this is not going to contribute anything there. Right? And that's a good thing. Okay. Let's see. We looked at that. We looked at Backprop. Okay. Here's one generalization of neural networks to something called convolutional neural networks. Convolutional neural networks are, as we saw, a lot of times your input can be a 2D signal, right? It could be a 2D signal or it could be a 3D signal with 2D with multiple channels, red channel, green channel, blue channel, or if you're doing multispectral imaging, sort of multiple channels here, right? If you think about any reasonable sized input, 400 by 600 or whatever, right? If you stack it all up as a one input, it's going to have far too many pixels. And when you try to connect it to a hidden layer, you will have far too many weights. So just an illustration of that. Right? Now think about it this way. Here is an image, and let's say this is 300 by 400. Right? If I string this up as a really long vector, this is my x, right? This is 1.2 into 10 to the 5. That's the length of this vector. Right? 2 zeros, 4, 5. Oh, 6 into 10 to the 4. Jeez. Oh, that's right.
5 point.
1.2 into 10 to the 5.
Point. Yeah.
Yes, that's correct. Okay. So that's the length of this vector. This is the input layer, right? And let's try to connect it to a neuron, right? The hidden layer. If you connect every single pixel to one neuron, suddenly the weights that you have to learn are that many, just for a single neuron, right? Try to have another neuron, you have that many more weights. Another neuron, that many more weights, right? So this is just far too many parameters and this is a small sized image, right? Let's assume that there's a third channel of RGB, this thing rises even more. So we can't actually learn that many. Despite claims that we can learn extremely deep models, this is hopeless, right? This is not going to work. And so you make this, right? So that's what I was illustrating. Every single pixel connected to every single hidden response, there are just far too many parameters. But you can make this assumption. So here's assumption number 1, that this is a hidden response, and it actually doesn't, so this is called spatial, forget what this is, locally connected, yes. So you actually don't connect it to every single pixel, you actually just connect it to a window of pixels, right? And there it drops the size. So let's say let's say you have 1,000 by 1,000 image, but you actually think of a filter size just as 10 by 10. So this is a hidden response unit that actually just looks at a 10 by 10 region of filters. That's assumption number one. So that reduces parameters. But the other way of reducing parameters, right? So this is you can start thinking of this as I have a filter and I'm going to multiply it by my image, and that gives me, right? So everything that I'm connected to is, you can start thinking of this as a 2D filter. I place it here, that gives me a dot product, that's the activation. As soon as you do that, at least the signal processing people in you should be jumping with the assumption of stationarity, right? They should start looking, right? There should be, like, why should a filter here be different from a filter here, right? Images are translation independent, and so the filter here should be the same as filter here, and therefore you end up learning basically a convolution, right? So a single neuron is basically just a filter that you scan across, right? So what you're learning now are these parameters, but you run them at various places, and so you actually get the same sized hidden response map as the input. But the number of parameters you have to learn are extremely small, maybe a 10 by 10 filter. Does that make sense? So basically the figure in your mind to think of is, instead of a fully connected, so this was a fully connected net, this was X, it was fully connected to a bunch of hidden units, right? Instead of this, what you should think of is you have an image, and I have a single neuron, which is a single filter, but I run it at multiple places, and therefore it leads to another image of the same size, ignoring boundary effects, right? Let's assume you can do convolutions all the way up to the boundary. So if this was 300 by 400, you end up with a similar sized response map, a filter response map. Does that make sense? And the argument goes, well, why learn a single filter? You can have multiple filters, right? So you can have one filter that does convolution, gives you a single response map. You can have another filter that does convolutions. And so this is basically the idea of a convolution.
So we have to overlap between each scan?
Yeah, so if you can choose on your, that's called the stride. But if you think of it as convolution, if the finest stride of stride 1, then it's overlap, right? So you have let's say you have a 7 by 7 filter, you move it by 1 pixel, so there's a lot of overlap. If you choose to not have overlap, then your hidden response will not be the same size, right? It will be shrunk. Because if you're skipping, then you're essentially subset.
I'll be treating like every single alone. I won't have results, good results.
Exactly. Well, say that again?
Do I will still have good results if I did that?
Actually, you will. So I'll talk about that in a second. So you actually, typically what people do is they actually do fine strides. So they actually get a convolution map, and then they do subsampling or pooling. And I'll talk about what pooling is. So this is essentially what it looks like. You have a bunch of these filters giving you a bunch of these. So this is one filter giving you a bunch of responses, and you can do this thing called pooling, where you just average or max pool the responses in a window, and that gives you a smaller response, right? So in a way, you should think of this architecture as an input comes in, I apply a single filter, that gives me this map. I apply another filter, that gives me this map. And so let's say I applied 6 filters here. They give me 6 maps of the same size. And then I subsample this. I can subsample by averaging things in the local window, or I can just subsample by taking one thing in a local window. And so it reduces the size of this input, right? Now I can take another filter, convolve, get this. So all filters, all convolutions, I can get a bunch of filter maps here. I can subsample them again. Ultimately, usually in convolutional neural networks, your input, which started out as a large image or a large multispectral signal, becomes a small enough thing that you can concatenate it into a fully connected layer. Right? So ultimately, because of the subsampling and the pooling layers, it's becoming small enough that you can later connect it to a fully connected. I didn't show you how, but the signal processing people in you know that convolutions are essentially a matrix multiplication, right? It's still a linear operation. So linear operation, non-linearity, linear operation, non-linearity, and the same thing here, right? So you can actually do backprop through this entire network. we know how to do gradients of this layer with respect to everything forward, and you just have to derive the same thing for these surfaces, right? And that's how these things are trained. You take an image, convolve all the way, produce a response. What did we want for this image? Let's say we want a digit, compute an error, compute backpropagation. Now you have an update for each one of these weights, including the filters. Take a step in that direction, keep going. Right? Does that make sense? And that's what this figure that I was trying to show you is. This thing is essentially, not essentially, this is the conv net, this is the input, these are the different hidden responses in layer 1, these are the responses in layer 2, so they're becoming smaller until they become so small. And this is why it's actually interesting that the filters you end up learning at these layers are actually gradient-like filters. Okay. Let's see if I have. Let me come back to this. But here's a. This was a paper in ECCV by Matt Zeiler and Autoencoders. This was nominated for the Best Paper Award. There's an excellent visualization here where they had a large convolutional neural network. The input was images, the output are categories, 1 in 1,000 categories. This is called the ImageNet challenge. And what they're visualizing, these are the filters, and these are the patches that produce the highest activation for these filters, which is a way of visualizing. So this is the filter, it looks like oriented, the first layer looks like oriented gradient type filters, right? And these are the patches that you can think of it, this is what it's learning to detect. Right? This is the patch, out of all patches and all images, that produces the highest activation for this filter. That makes sense? So you can see that they're essentially oriented gradients, right? This is layer 1. Layer 2 starts to learn some interesting structure, right? This one, so the second one, you look at this, it's actually a filter that's learning circular objects. Right? Essentially circular objects. This one is a wheel, this one, I don't know what it is, but it's ended up becoming a circle detector, if you will. Even though you never hand-coded a circle detector. All you said was, here's a convolutional neural network with multiple layers that needs to produce the output of a person or a dog. Right? So this one has long, thin structures. That's only layer 2. You get to layer 3, and this is sort of a cell-like structure that it's learning to detect. These ones are parts of a car, right? So the tires clustered together here. So the way to think about this 3x3 is the filters, and these are the images that produce the highest activation for these filters. Here is parts of a person that it's learned to detect. A lot of these are fired by people in a particular pose.
So the size of the object doesn't matter.
Say that again?
The size doesn't matter.
To what?
You have these patches, right? On the
Yeah.
right. So if those patches were a little bigger, so does that matter?
Yeah, so I actually didn't talk about this issue, right? If you think about this architecture I showed you, it actually assumed that all input is of the same size. So there's a scaling issue that you have to deal with. One way of dealing with it is you just rescale all your images to the same size. You may actually end up scaling your image. This is a very common trick in computer vision, right? You create what is these scale pyramids. So you upscale your image, downscale your image, and you may actually get different crops of that and run it through the network. So you're actually looking for that piece in different scales. So layer 3, layer 4, and 5. So by the time you get to sort of layer 5, it's become extremely sophisticated sort of parts of objects, if you will. So this is the eye, there's the dog face here, there's sort of flowers here. If you think about it, the reason why this is interesting and exciting is this is it took us many decades of computer vision to try to hand code a hierarchy of parts that, filters are important that produce curves or line segments and basic shapes, and parts of objects come together to form objects, and different objects come to form together scenes. And this thing, without any of the hand coding, seems to be learning a lot of the same structure. And the power is actually coming from the fact that the architecture is an extremely large learning machine. There are a lot of things that it can learn, and there is a lot of data. Right? This was trained on roughly 1.2 million training images that are part of ImageNet, and that's enough data for this network not make it overfit. That make sense? Okay. Let's skip over something. Yeah. So here's the illustration. You should think of it in your mind. It used to be that this is what machine learning consisted of. That there was some domain, there was an image domain, some domain expert wrote this feature extractor and gave you some representation. And this is where we came in, right? This is where machine learning started. And that has changed with a lot of this thing called representation learning. And that's actually a better term for deep learning than, one of the problems with deep learning is it's a straw man argument. Nobody ever gets up and says, no, I really want to do shallow learning. Right? It's like, nobody's saying that you shouldn't do deep learning. Nobody's making the opposite argument. But to give them credit, the argument being made here is that there is an input and the representation of that input should not be left up to domain experts. Right? And that's, if you think about it, an extremely cocky statement. But we know better that there is some function that we can actually extract representation to do end-to-end task learning. Right? That's what a lot of these things do. That give us raw data, and if we can train a large enough system, it will learn to extract the representation that does none of these tasks. Okay. On that note, I'll just do one more thing. Here's an interesting idea of a neural network. This is called an autoencoder, as in encode yourself. Right? The idea is your input is X and the output is also X. So it feels trivial. Well, I just have to draw one edge here to that and set identity weights. And that's where these come in, right? You do not get to see the input directly. You have to map it to some hidden representation, and that representation has to have a lower dimension. Right? So there's some low-dimensional representation. This goes here, and this has to then generate the output. And the idea is that so this is X, this is X hat, this is what you predict, and your loss function is squared loss. How much will you be able to predict yourself? Right? And the idea is that you can think of this as a dimensionality reduction algorithm. Right? You're learning to reduce dimensionality so that you will produce yourself. And we'll talk about this later on. So, yes. No, go ahead.
So basically, do the backdrop on that one to do like the optimal minimized set.
Yeah. So you can still do, as he said, you can do backprop on this, right? There are weights here. Like nothing changed. Everything that we derived, it's just the output became the input as well. Squared loss was the same thing. You could still do backprop on this.
So how to decode it?
How to decode this?
Yeah.
But these weights are already decoding for you, right? So you should think of this layer as the encoder and this layer as the decoder. So one set of matrix multiplication and nonlinearity takes you to a hidden representation, and another set of matrix multiplication and either nonlinearity or lack of that can take you to an output representation. Does that make sense?
But can't you, like, if I just give you the predicted output, can you generate the actual one? Like, if I give you x1 hat, can you get back x1?
If I give you x1 hat, can you get x1? Your network is trying to minimize the squared loss between x1 hat and x1. So optimization issues aside, it can do no better than the output it just gave you, right? Does that make sense? Okay. And again, when you apply these things to images, so the input is an image and the output is an image, and you end up learning these sort of low-dimensional structures, which again end up looking like basically filters, right? So you should think of this as, if I had to compress an image into a small number of dimensionality, what I would do is I would sort of project it on each one of those filters and use those coordinates as my features. And then, of course, there's the idea of stacked autoencoders, which is if you like something, apply it twice. Which is if you can go down from x to x hat, you can take your hidden representation and try to predict that again. Right? So why stop at 1? So you went down from 6 to 4 dimensions. These are your 4 dimensions. Try to go around 4 to 3 and try to predict yourself again. So now you've reduced dimensionality even more. And these things are typically trained layer by layer. Let's see, and there's sort of interesting work that shows that these layer by layer things also end up learning interesting structure. So the initial stacks end up learning sort of edge type filters and higher level pieces of objects. And ultimately you can sort of use these last layer features to do classification on top. Right? So you can sort of compress feature reduction, and then do classification. Okay, so let's stop here. Basically, we are at this point done with neural networks. We expect you to know sort of the basic ideas of backpropagation and representation. The exact sort of in most of these things, nobody remembers the exact gradient update rule for different kinds of layers till you actually end up designing a new layer. Right? The thing that you need to take away from all of this is that if you just do it for one type of layer, a fully connected layer to multi-layer perceptrons, you'll get the basic ideas of how to do it for a new layer that you may be defining for your work. Or even if you are using neural networks for your particular task, it's good to know what Backprop is doing at a later. Okay? All right. Thanks.